So here is a lecture about how SSL works and how to protect yourself against man-in-the-middle attacks. Please do not skip this lecture even if you know SSL. I will go over the basics, but trust me, there will be some new content for you. So, SSL refers to Secure Socket Layer, and it's used to encrypt connections. And TLS refers to Transport Layer Security, which is a newer version of that protocol. And nowadays, even though it's almost only TLS certificates, people still refer, including me, of it as SSL. So if you hear me say SSL, I mean TLS, and it's just everyone does that, so don't get mad at me. So public SSL certificates are issued by something called the Certificate Authority, and you have many public certificate authorities such as Komodo, Symantec, GoDaddy, GlobalSign, DigiCert, Let's Encrypt, and so on. And when a certificate is issued to you, it has an expiration date that you will set, and then you must renew it before it expires to keep your service up and running. So, how does SSL encryption work? Well, you have a client and a server, and they need to talk to one another using a secure channel. So they need to use SSL encryption. The thing is, using asymmetric encryption, which is the basis of SSL, is very, very expensive. And by expensive, we mean expensive in terms of CPU cycles. So the least expensive type of encryption is symmetric encryption. It's much cheaper. But SSL is only for asymmetric. So the idea is that during the asymmetric handshake, which is the first connection between the client and the server, they're going to use and exchange a symmetric key that they will commonly share for this communication. And from that point forward, they will only use the symmetric key to talk to one another. So in this case, the asymmetric encryption of SSL is just used for the handshake, and then it's all symmetrical. So how does that work in detail? The client says, hello, here is my cipher suits, and here's a random thing. And the server responds, okay, here is my server random, and here is my SSL certificate. The client will verify the authenticity of the SSL certificate by looking up if it's correctly computed. And then if it is, it will send a master symmetric key that has been generated and sent, and that will be encrypted using the key that has received. And the idea here is that this secret will be able to be retrieved by the server and decrypted. And in case the client also has an SSL certificate, it will send it at this moment. So it's possible to have a two-way certificate where the client authenticates to the server and the server to the client. And then using the master key of the server, using the private key, the master symmetric generated key by the client will be decrypted, and we'll have a secure connection that is going to be symmetrical this time in place between the client and the server. You don't need to know all these details. The exam will not test you on this, but I want to make sure you understand how this handshake works, at least at a high level, so you get an idea of how SSL works, just for your knowledge, because I think as a solution architect professional, if you don't know how SSL works, that's a bit worrying, okay? But the exam will not test you on this exact knowledge. Definitely not. But something it may test you on is SSL SNI, for server name indication. So the idea is that SNI will solve the problem of loading multiple SSL certificates onto one web server only. And that will allow you to serve multiple websites from that one web server. It's a newer kind of protocol, and so it requires the clients to indicate which hostname it's trying to connect to during this initial SSL handshake that we saw. And then the server will find the correct certificates, or it will return a default one if it doesn't find one. And so this works for the ALB and the NLB, which are the newer generation load balancers, and CloudFront. It does not work for your classic load balancer, which is older gen. Very important to know. So we have our ALB, and it needs to be connected to two target groups, which are connected to different host names. The first one is www.microbe.com, and the second one is domain1.example.com. So we're going to load two SSL certificates onto our ALB, but it could be more. And so one SSL certificate will correspond to the first target group, and the other one to the second target group. The idea now is that a client who has SNI compatibility says, hey, I would like to connect to www.microbe.com. And the ALB, because it has SNI enabled, will use the correct SSL certificates, and then it will redirect to the correct target group, and we'll have an encrypted connection. But in case we ask for, obviously, another domain, then the ALB will be smart enough to get the other SSL certificates and connect to the right target group. So SNI is extremely important as soon as you have multiple SSL certificates. If you have a CLB, it doesn't work, so a classic load balancer, and it doesn't work with SNI, then we cannot use one CLB behind multiple applications. You would need to have multiple CLB for multiple ASG in order to get this architecture working. Okay? And next, extremely important, how to protect yourself against SSL man-in-the-middle attacks. So how does it look like? We have the good server we're trying to reach, and our user is trying to talk to it, but there's a pirate server in between. And because it's HTTP right now, it can intercept the packets and change them at will, and so it's in the middle and it can see the secrets and so on. It's really, really bad. So this is never happening on the web because there's almost no more HTTP available. But if you do have HTTP on the web, be very careful because you can be a target of man-in-the-middle attacks. So now the good way is to use HTTPS. So we have the same kind of architecture, but this time the pirate server will try to send a fake SSL certificate to the user by decrypting the packets from the good server and re-encrypting them and maybe changing them. And so if the user is not infected, it's going to detect it's a fake SSL certificate and not react to it and just say, okay, I'm not communicating with that pirate server. But in case the pirate server did manage to get onto the user's machine and make the pirate certificate trustable by the user, then the user will say, oh, this looks like it's the certificate I trust, and the pirate server has successfully done a man-in-the-middle attack. So how do we prevent a man-in-the-middle attack? Number one is do not use public-facing HTTP servers. Use HTTPS. That means that you leverage SSL and TLS certificates, and that means that the content is encrypted between your client and your servers. That doesn't prevent the second vector of attack, which is to have a DNS attack. So if you're using a DNS that has DNSSEC enabled, that means that the DNS is going to be protected against the type of attacks as well. Why? Well, when a DNS server is hacked, or it's possible for a pirate server to forge a DNS response and to send your clients to the wrong target server. But you can protect against that by having your domain name configured with DNSSEC. So Amazon Route 53 supports DNSSEC for domain registration. And as of December 2020, it also supports DNS security, DNSSEC for DNS service itself using KMS. So both domain registration and the DNS service are now DNSSEC compliant on Route 53. You could alternatively run a custom DNS server on EC2, for example. One of them could be Bind, which is the most popular, but you have other ones such as DNS Mask, Not DNS, or Power DNS, and configure DNSSEC directly on your custom EC2 instance. But right now, there's a change, and Amazon Route 53 supports DNSSEC out of the box as of December 2020. That used to not be the case. All right, that's it for this lecture. I hope you liked it, and I will see you in the next lecture.